Thank you. I'm honored and happy to have the opportunity to contribute to here. And I'm very grateful, deeply grateful to the organizers and the facilitators and all the other participants in this interdisciplinary summit. It's not only interdisciplinary, what's also impressive and quite unusual is that it also is the stretching across many different sectors of society. And I think that's exactly what it takes for a real transition into sustainable and climate resilient society, which is a key message in the protocol that is drafted for this conference. I've been asked to talk about methane and climate. Methane is a powerful greenhouse gas. It has only a 9-year residence time in the atmosphere, and the continuing releases of methane to the atmosphere now makes it accountable for 1/3 of the global warming that we're experiencing right now. Deep reductions in methane by 2030 is an absolute requirement to lower peak warming, to reduce the risk for climate overshoot and to reduce the extent of climate overshoot, and also to lower our reliance in the future or now on mechanisms to catch CO2 from the atmosphere, which is a very large technological challenge to do on a global scale. There are signs of worry with methane. It's increasing in the atmosphere still now, and the increase seems to be accelerating. There are also signs of hope. It seems like we are gathering to also, in many programs, to forcefully mitigate anthropogenic emissions of methane. I'd like to be clear from the onset here that cutting methane this decade is essential if you are going to honor the 1.5 or even the 2-degree target, which in a sense we can read as a promise to coming generations. It is not enough to cut methane, as Gabrielle just mentioned too. We must also cut other short-lived climate pollutants and carbon dioxide. And the way I think all of us here see it, it is the only way for us to prevent the suffering for humanity from the climate catastrophe. Methane matters. It is a very important greenhouse gas. It's important, this factor, that it is relatively short-lived in the atmosphere. That is the sort of the window of opportunity to limit warming to the climate targets and thus avoid passing important climate thresholds. It might be interesting to know that the methane that's being emitted to the atmosphere is about half-half from natural sources and from anthropogenic sources, and that an estimated more than 60% of the methane emissions comes from the tropical region. But the uncertainties regarding the sources is very large. But we certainly know enough to do something about the anthropogenic sources. There are signs of this climate-enhancing feedback of increasing releases from tropical wetlands to Arctic permafrost. I'll talk a little bit about that. The global sustainability research program, Future Earth, together with the World Climate Research Program and the Earth League, is in recent years putting out an important document which comes out with a higher frequency than the IPCC reports, which are of course extremely essential. This annual report presents 10 new insights in climate science of large value for climate policy. A key insight last year was on the climate overshoot. Science is there to show that it's fast becoming inevitable and that it's absolutely essential to limit climate overshoot. One of the insights that we're working on this year is on these soaring methane levels and on different aspects of that, such as underestimation of both anthropogenic and natural emissions and inadequate regulations. In fact, it's only 16% of anthropogenic methane emissions that fall under any type of regulation. These new insights is launched annually at the COPs by the UNFCCC president, so it has some impact. Okay, but you might ask, so if we miss the targets and have climate overshoot, does it really matter if we then swing back at net zero fossil and we're able to do this air capture of CO2 and get us back down? If we look at these graphics to the left there, which is in an editor from the editor in Nature Geoscience about last year, it illustrates that it does matter. Well, I'm going to talk about that it matters, but what it does illustrate is the lower curve there in the lower panel shows that to honor 1.5 degrees, we have to have massive reductions of emissions of all greenhouse gases from now on. If we don't do that, but if we wait some years, the blue and the red curves there in the lower panel, and then have rapid reductions to net zero fossil, you see in the top one, we will have climate overshoot. And then to bend the curve later at in some unknown place above the climate target takes these negative emissions, continuous removal of CO2 from the atmosphere. These are very costly techniques. They are not really at place and haven't been shown at scale yet. So we shouldn't put too much hope into that. Better would be to mitigate now. When we reach this space beyond these climate targets, which are there because they also correspond to thresholds in the climate and Earth system, we enter unknown territory of Earth system functionality and unknown consequences for humanity. So there are many risks with climate overshoot. One is on irreversibility. So even a temporary climate overshoot, if we are to then press it down to 1.5 degrees over the coming century or so, we might during that time have irreversible effects, such as that the Amazon might reach a point where all of it by itself will disappear. We might have unstoppable melting of glaciers in Antarctica and Greenland, slowdown of the global ocean circulation, and a self-enhancing release of methane from wetlands and permafrost. So the methane levels are soaring. The methane levels in the atmosphere has increased since the Industrial Revolution, quite substantially. But then you see here that around year 2000, it reached some kind of steady state, which lasted for 7 or 8 years, maybe a decade, and then it started to increase again. The worrisome thing is that whereas we had sort of the concave increase up to that point, we now have a convex increase. So the increase is accelerating, and that's what we call the soaring methane. Same thing is shown in this blue graph here. That's the methane concentration in the atmosphere, increasing rapidly. The red one is of a sort of a personality of the methane that is there. The carbon-13 to carbon-12 isotopic composition. We don't need to get into what an isotope is. Think about it as a fingerprint of the sources of the methane. And it's decreasing rapidly in the recent decade. There's an isotope plunge, we call it. And the right one shows this on a longer time horizon. You see that before the Industrial Revolution was around -49, and then it's been increasing ever since to a peak some 7-8 years ago or something like that. When we have a rapid shift, a regime shift in the isotopic composition of atmospheric methane. It's a big change. What's going on? What is behind this changing emissions that is reflected? Well, a decreasing isotopic composition of methane in the atmosphere signals that it's no longer the relative increase in fossil fuel contributions, but now there is a microbial source of methane that is overshadowing that. There could be many sources. It could be anthropogenic sources, such as rice paddies, wastewater systems. Definitely tropical wetlands is a big source. I'm going to illustrate this with the permafrost around the Arctic. This is an enormous pool of reduced carbon, the largest pool of reduced carbon on the Earth's surface. It holds as much carbon as 300 times the carbon in the methane in the atmosphere, and it's thawing rapidly. The Arctic has an amplified warming. In the context of the Paris Treaty, I try to illustrate with the graph to the right here. The gray part of those bar graphs is this carbon emission budget that remains if you're going to honor the Paris Treaty. The green fields there is what permafrost scientists estimate will be released from thawing permafrost this century. So even if we honor all the commitments in the national determined contribution and push them down so we reach the Paris Treaty, we are going to climate overshoot. That's because of that single feedback. And on top of that, I added red there, is this permafrost underneath the ocean in the Arctic, the subsea permafrost, which is even less well understood, and its potential for collapsing methane hydrates. What we're talking about is a self-enhancing feedback between amplified Arctic warming and accelerating release of methane from thawing permafrost. To illustrate, if we reach 2-degree warming, estimates are that greenhouse gas release from thawing land permafrost this century will be of the same scale as emissions from the entire European Union. We're triggering that release. Now I'm going to talk very briefly about subsea permafrost. So we've been pulling together based on a lot of expeditions we've been to in the Russian Arctic and across the Arctic, and from other researchers to methane in surface seawater. And it's elevated relative to what it should be if it was only equilibrated with the atmosphere. And it's particularly elevated in the world's largest continental shelf sea, the very shallow East Siberian Arctic Ocean, which is also where we have subsea permafrost. So we think there's a link. So to the right here, you see that over this very large scale, it's the world's largest coastal seas. There is methane levels that is 10 to 100 times that what you would expect from atmospheric equilibration. When we go back there and we do drilling 50 meters down into the ocean bottom and on nearby land, these two systems were similar before the sea level rise. Both started about minus 18. The one that's now under warming seawater has reached 0. So it's thawing. And it's thawing much quicker than land permafrost. So subsea permafrost is more vulnerable than the land permafrost, but it's the one that's mostly discussed. There's good news and hope, and it is the methane mitigation initiatives that are there. The Global Methane Pledge is a very important one, proposed by President Biden of the US and President Ursula von der Leyen from the EU, but many, many joining. And the promise is that we're going to cut global methane by 30% by 2030. And it will shave off as much as 0.2 to 0.3 degree warming. And that's a lot. And we would like to get everyone on board. We're in this together. We have to work together. The way it's going to happen is largely through fossil fuel. Methane release from fossil fuel reduction we're going to stop. There's good economy in that. Those are really low-hanging fruits. But it's also possible to reduce methane release from waste in agriculture. Mitigating methane is actually quite cost-effective. Leaky gas pipes and from production facilities and so on, if you don't lose that, that's a commodity. That's an economic value. So it should be doable to do that. There are also co-benefits between climate, many aspects of human health, and for food production. So mitigating methane, a doable thing. Final slide here, just a few messages. Climate overshoot and methane. But to face it, we're about to miss these targets. The way we're going now. We'll get into climate overshoot then. That would demand enormous CO2 capture programs. I don't know exactly how they will happen. The better would be to try to mitigate now. We have to adapt and prepare for that scenario too. We have to do everything at once. The thresholds with the climate that are passed in the Earth climate system with climate overshoot, some of them are irreversible. So those that we will have to live with for a very long time. Methane mitigation is a low-hanging fruit. The urgency is now. And as the protocol says, there is a need for speed. We have to act now, and we do have a good job to do. And I was quite inspired, I must say, by the real decision makers that's spoken here earlier today that shows that there are programs. There is real action happening. So I think there's hope, but I think we should do what we can. Thank you very much for your attention.